Good morning, good afternoon, good evening. Thank you for joining the Stantec webinar series today on hazard considerations in the design of wastewater treatment plants. Pat Coleman from our Toronto office, Dr. Pat Coleman, I should say, is going to be talking specifically about Hazop, Swift, and OPMAN. A couple of housekeeping items before we get going. You'll be muted during the presentation, but you are welcome to ask questions using the GoToWebinar questions function. I will read those at the end. I will also open up your mics and give you the ability to either comment or ask a question live towards the end of the presentation as well, if you're interested in such a thing. There will be a recording of this presentation. It'll be posted on our website. You'll also receive an email from GoToWebinar with a link to that if you would like to view it offline. And everyone will get a certificate of attendance to submit to your certifying agency for potentially PDH credits. With that, I'm going to turn it over to Pat, and he will lead us through the presentation.
Yeah. Well, thank you very much for letting me speak on this important topic today. Can you hear me okay? Everything fine?
You sound great, Pat.
Okay, great. So my passion for this topic comes from my belief that no one should rely on luck to go home at night to their families. And I know you agree with me because you're here on this webinar today, and I appreciate that. So therefore, the objective of this presentation is really to provide you with more tools to design safer and more resilient facilities. So the construction, commissioning, operation, and maintenance of our facilities are safer when we think safer day one. Now, this statement is true. When we design, when we are designing something that will be procured, built, commissioned, and operated, from day one, we concern ourselves with value and quality. But from day one, we also focus on safety. We load the dice, so to speak, in our stakeholders' favor. Now, what's fascinating for me is when faced with a problem, we always usually institute checks first as our first response. And that's no difference with safety and design. Instituting checks, though, is just the start. Long term, we need to address why our designs are not as safe as they could be. That said, most of this webinar is actually going to be on checks, but I just want to leave that thought with you. So this is what I'm going to talk about. Now, one person who has influenced my thinking about safer design the most is Trevor Klecht. He's not a household name in the water industry, but well known in the chemical processing industries. I'm going to introduce you to Trevor Klecht in this presentation as a means to discuss at a high level the whole issue of safer design. We will then look at three commonly used methods to check designs in the water industry: Hazop, Swift, and OPMAN, and then we'll wrap it up. So let's talk about Trevor Klecht and safer design. Now, Trevor Klecht's story is very similar to my story. As I suspect, it's also very similar to yours. So Trevor Klecht was an industrial chemist. He joined the Imperial Chemical Industries, ICI, after World War II. He started in the laboratory, moving to the factory floor, and ultimately to managing chemical processing plants. Somewhere along the line, his boss asked him to take on some health and safety responsibilities. Trevor was reluctant because, as he said in his biography, he just thought it as more paperwork. And I think we've all been there. Now, at that time, he had a colleague who was trying to apply a business method to engineering design. This methodology uncovered numerous issues in a design that luckily they were able to address before the new plant was built. ICI, their employer, was suitably impressed. This methodology became what we know today as Hazop. Trevor embraced this methodology. In fact, he published the first book on hazard and operability studies. Now, his responsibilities for health and safety continued to increase. He analyzed a number of failures and came to the conclusion that he saw the same accident occur every 5 years. He realized that unless the company formalized what they had learned from accidents, people would forget. This ultimately led him to publishing his book on inherently safer design. He took lessons learned and results of Hazop studies and developed a methodology to produce safer designs. So this figure on this slide is a summary of Trevor Klecht's philosophy. We design to be safe. That's the intent. We check our designs to ensure they are safe. That's the check. And we learn from our successes and failures. That's the learn. This is the virtuous circle we should all aspire to achieve. Now, interesting enough, Trevor Klecht lived to the ripe old age of 91, but just before his 90th birthday, he was quoted of saying, "I've saved a lot of people's lives. That's something I can be proud of." That's a long ways from the man who originally thought that health and safety was just a lot of paperwork. The ICI 7+1 diagram is another way to view this philosophy. The top row, in gray, outlines the stages of the project from inception to demolition. The bottom row outlines the types of checks performed at each stage. The 3 studies we will talk about occurred during detailed design. You can see that they developed a very comprehensive system of checks. The idea that an organization must learn and design with a safer intent came later. Another way to view this philosophy is to look at the hazard triangle. The 3 sides describe our relationship with a hazard. Ideally, we want to identify and mitigate a hazard before it occurs. I mean, that's why as a young child, you're always told to look both ways before you cross the street. The 3 studies we will talk about are part of that process. However, if a hazard is missed and an unfortunate event occurs, we need to extract from that event knowledge we can use to prevent the event from occurring again. However, it's not enough to identify and investigate hazards. We need to remember and manage them during design and after the facility is built. So on the bottom, you can see how we encapsulate both what we learned and our values in our procedures and our training. So let's focus on identifying hazards. So all the methodologies pretty well follow the same 4 steps. Identifies a cause, assign a likelihood. So look for a reason that something's not going as you would expect it to go. Characterize the consequence of that failure, always without looking at what safeguards are already in the design. Identify what safeguards are in place now and decide whether, well, do we need to make additional changes? And then out of that come a set of recommendations. So I'm going to introduce you to 3 techniques. This picture is taken in the early 1900s of what we think is the UK Royal Commission on Sewage Treatment, standing in front of a rock media trickling filter. And the reason I'm showing to it because I really think the personalities of these 3 individuals that we've circled in white really summarize the personalities of the 3 methods. So if we look at Hazop, the man with the top hat, you would expect someone wearing a top hat, holding the drawings, obviously the boss, would be much more rigorous and rigid, much more looking at the minor details. If we go over to the man with the bowler hat, who's we think the superintendent, well, he looks much more pragmatic. Well, for one, he's not wearing a top hat at a sewage plant. And you would expect that, well, he would have the same sort of rigor in some ways, but I think he'd be a bit more adaptable, a bit more flexible, a bit more quick on things, would see things much more from a systems point of view. Now, if we look at the man on the left with the cap, well, just look at the way he's standing. You can see this is a man of action. He's practical, tangible, focused on his pretty well on his day-to-day activities. That's how he would see this whole thing. So that's very much the personality of OPMAN. So think of that as we go through, because these three people will come up again and again, because I really think they capture the personality of the methods. So let's start with our man with the top hat. So Hazop, why do we do it? The reason we do a Hazop is to identify hazards or opportunity problems in the design before the facility is built. So a perfect Hazop study is one where no hazards are found. A Hazop follows the process flow using a mature set of P&IDs using a checklist. The outcome is a list of actions. Very heavily process-based because it comes from the process industries. This is what we call a technique diagram. So you can see down the column process, input, output, tools, skills, and effort. So what you need to take from this diagram right now is three things. Obviously, you need a firm facilitator to keep the team on track. The lead designers must be present to explain the design and answer questions. And the participants must commit to being there, as the process is mentally tiring. So how does it work? Well, the facilitator steps the team through a checklist for each node. For example, the attribute may be flow rate, which I circled, and the guide word may be no. The team then decides if there could be a no flow in this line situation. If so, what would cause it? They note that there is a manual isolation valve with no indicator to SCADA. For example, if this valve were closed and no one knew about it, there would be no flow to the aeration tank. The consequence in that case would be the flow would go to the other tanks. The team then would assess this risk and decide if they can manage it given the current safeguards in place. If not, they would require a change in the design, i.e. a position indicator to SCADA for that valve. Let's step through a simple example, and I think it'll become much clearer. So we're in a Hazop. We pull up this simple P&ID. The process is described to us, right? It consists of a buffer tank followed by a feed pump to a centrifuge, but then feeds another tank, and then the sludge is pumped to the digesters. And then the liquor is then sent by gravity to somewhere else. So that's our very simple process. Once the process is described, the facilitator would then split the process into nodes. And you can see there would be three nodes in this case. Node 1, the buffer tank. Node 2, the suction pipe work and pump. Node 3, the discharge pipe. Now, what's important to realize, going back to our man with the top hat, is now we're going to really focus in on the nodes. We're not looking at the system as a whole. Then we have to agree on a property. So here's the Hazop list. Now, the facilitator will go through everything on this list. This is why it's so tedious. In this case, we're at level. We agree that the property is level. We're talking about level in the buffer tank. Then he selects a deviation, in this case, lower. We're talking about an unexpected low level in the buffer tank. What's the cause? Inflow less than outflow. Okay, so we got a synchronization problem. Consequence, well, if the level passes through the mixer blade, we will damage the mixer. The safeguards that are in the design at the moment, well, there is a soft inhibit through SCADA to shut off the mixer once the level approaches the blade. The team wasn't happy with that. They said, no, not good enough. We need to have a hardwire inhibit. So that was then assigned to the designer to put in. Another cause is the tank is offline. Well, if the tank's offline, the mixers and sprays could still operate if it's not properly shut down. Well, there are no safeguards for that. That's really down to operations. So the recommendation is that you need to check, and if it's not the case, there has to be a standard operating procedure on how to take a tank offline, and that was assigned to the owner. So that's Hazop. So again, we look at a line or a vessel, not the system as a whole, and once a node is agreed to, you systematically go through the guide word list to generate the documentation, and you go through every guide word. So it's based on nodes, it's rigorous, and it's rigid. And that's why it's so good for high-risk applications. But you have to ask yourself, is this the right application for everything we do in wastewater and water treatment? That leads us to our next question, Swift. So now we're talking about our man with the bowler hat who's a bit more agile. Swift looks exactly like Hazop when you step back. Same sort of goals, same sort of report. In fact, you can use the same software. The difference is how it looks at the process and how it comes up with risks. So Swift, one of the advantages of Swift is that it doesn't have to be, it's not totally process-based. Because it breaks down and looks at systems and subsystems, you could have a situation where it looks at something like compressing biogas prior to boilers, which is very much a process type thing, and you would lean much more in the what-if analysis towards process-related Hazop type things. Or it could be removing screening bins from headworks, which is much more logistics. So really the hazard is in the whole logistics of when the truck comes to site and how it gets access to the bin and lifts the bin onto the truck and then leaves the site. So Swift allows you to look at both types of risks. So two things you need to notice from this technique diagram. A Swift is similar requirements as a Hazop, except it takes less time, about half the time. And at the core of the Swift is a what-if brainstorming exercise, rather than that node by node level, no flow type thing. Therefore, the facilitator of a Swift has to be quite agile because you've got to walk a thin line between order and chaos. So let's go back to our example. So here's our P&ID. We go through the same process, explained to the team how this is supposed to work. We then break it into subsystems, right? So the Hazop broke it into 3. In this case, the Swift broke it into 2. So in this case, the subsystem 2 is the suction pipe and discharge pipe and the centrifuge pump. And subsystem 1 is the buffer tank. The difference is in how you come up with the risks. So you go through a what-if framing thing. So the facilitator chooses what to brainstorm on. So it says, okay, let's brainstorm on plant or control system failure. And in this case, they came up with 2 what-ifs. What if the level sensor is out of calibration? Well, then we don't know if there's a high or low level in the tank. Now, these tanks act in parallel, and they have a pipe that connects them with an isolation valve. Well, they said, okay, the safeguard was to use the level sensor in the other tank because the level in the 2 tanks should be the same, and they have a backup level switch. However, the team said, hold on a minute. What if you've closed that isolation valve because you got a tank offline? You know, you have that isolation valve closed and the levels aren't the same. So then they said, well, you need to have a position indicator and you need a discrepancy alarm. Similar, what if a mixer fails? Well, if a mixer fails, solids settle in the tank. Well, that's not that bad of a risk. You can continue to operate and thicken up the sludge with the centrifuge. Now, the team said, okay, well, we need a SOP in place to maintain the mixers because they're quite critical. And they said consider a recirculation pump, which the owner and the team, the designer said, well, no, that's not a good solution. But they did say review the critical spares list, because if the mixer goes down, we can operate a while with it offline, but we need to get it back online quickly. So that looks at a SWIFT. So they're very similar. SWIFT looks at the system and subsystem. Hazop looks at a line or vessel, not a system. With SWIFT, you brainstorm possible failure modes with what if this type questions. With a Hazop, you systematically work through a guide word list and generate documentation for a single node. You can do this earlier in the design with a SWIFT. With a Hazop, the design has to be quite mature. Hazop is very exhaustive analysis compared to a SWIFT. The SWIFT is quick and easy to implement, takes about half the time as a Hazop. Hazop is time consuming and resource intensive, but it's very thorough. But that leads us to another problem. This isn't good enough. It just isn't. There's another type of hazard we must manage. The hazards that impact the well-being of our staff. Short-term hazards and long-term ergonomic type hazards. Now, OPMAN came about partly because operations at a major water company in the UK said, this is fine, Hazop and SWIFT, we're on board, but you're not addressing the risks that we face every day. So let's look at OPMAN. So OPMAN, why is to ensure that the facility is safe to operate and maintain. It follows a P&ID and 3D model using a 5-question checklist. And you answer back on a scale 1 to 5. Interesting enough, it kind of fell out of favor until we started doing 3D design. And with 3D design, it became much more important to operators because they could actually see the situations they were in. So here's the technique diagram. And there's just 3 things you need to take from this diagram. Number 1, the 3D model is important. If you have it, use it. Secondly, the team just scores an item on a 1 to 5 scale. It's not a, once they reach consensus, it's either a 1, 2, 3, 4, or 5. The second is a facilitator must keep the momentum going, as the method looks at every valve, pump, tank in the design. So you would think it would take a long time, but the facilitator keeps it moving, and the scoring 1 to 5 makes it go much quicker. So to give you an idea of time, we found that we could do a SWIFT and an OPMAN in the same time on a design as if we'd done a Hazop. So this is an example from the City of Toronto. Now the client and the facilitator sit down before it, and they set this table up. So this is how the table would look for the City of Toronto. This isn't how the table looks for everyone. You set this up based on what's important. But if you look at the column beside the A, B, C, D, E, F, you'll see the major topics do not change. Access for operation, access for maintenance, mechanical isolation of individual components, electrical isolation, equipment removal, process implication. Oh, sorry. And then if you look along the top, there's the scoring. So it's either acceptable, but could be improved. So you say, well, if you did this, it would be an improvement. Unacceptable, go back to the design board, but we don't think it's major. Unacceptable, you're going to have to do some significant redesign. Or number 5, you didn't provide us with enough information. You're going to have to come back to us and with more information, and then we'll make our decision. So it focuses on staff well-being. So assesses acceptability to the staff. They select a rating with the team. We provide a justification for the rating, particularly if it's unacceptable. And then sometimes they make recommendations. So there's a worksheet that's pre-populated before the meeting from the P&ID. So every valve, etc., is listed on the workbook. So you can see TAB STR V501 manual isolation valve, that's listed. And then there's a drop-down menu for each of them. Acceptable, acceptable could be improved, unacceptable, unacceptable requires design, insufficient information. And this is why it allows you to move quite quickly. So now we're going to talk about two types of risk, safety risk and ergonomic risk. So here's a sketch of a situation that came up on something I worked on once. So you can see there's the staff member, and he's looking up at a manual isolation valve. So they went ahead and they said, well, hold on a minute. Is it acceptable access for operation? Operation, no. If we have to close that valve, we're going to have to climb, and that's unacceptable. Maintenance, well, they said, well, you know, if we were going to maintain that valve, that's not very often, we would come up with a way of, you know, putting up something that was safe, and then we could maintain it. But, you know, you could improve it. Mechanical isolation wasn't an issue. The other three, electrical isolation, equipment removal, and process identification, were acceptable. Because if you close this line off, there were other lines that were available. So the team said, look, see if the valve can be lowered or rotated. If not, provide a remote faceplate or panel. Bottom line is we don't want operators climbing to reach anything. That's a safety risk. Ergonomic risks are a little bit more tricky. So let's think about it. So this comes from a standard that's written, prepared for shipping. And it shows where a valve wheel should be relative to a person's, the placement of the person's shoulders and waist. And so emergency operation, there's certain requirements, and then normal operation, there's certain requirements. Now, what we're trying to do here is avoid the situation where we develop long-term lower back problems, which have happened on some treatment plant site, or long-term respiratory issues that have also happened in other sites because of a maintenance issue. So we're looking at the day-to-day operation. So let's look at an example. Let's look at this situation. So we have an operator standing, valve number 1. It's a manual isolation valve. In order to get to that valve, they have to climb over the pipe. Now the hand wheel's too close to the wall. Every time they turn that, if they don't have gloves on, they're going to skin their knuckles. If we look at valve number 2, you know, the hand wheel is too high compared. So hold on a minute. So they're going to have to reach up to close that valve. That's not a good ergonomic situation. Number 3 was even worse. There's just no way you could reach that valve in a safe manner without standing or being in a very dangerous situation. Now you could say, why on earth did this even come into a design? Unfortunately, this is more common than it should be in designs, because the person that's designing back in the office isn't an operator and doesn't necessarily have gone through the thought processes of thinking about the person that's going to be closing, particularly things like manual isolation valve. So what was the solution? So number 1, they moved the valve and they changed the gearbox. So now it's like a steering wheel on a car. You know, it's in the right range. They doesn't have to climb over the pipe. Number 2, they changed the gearbox, turned it 90 degrees, again, like a steering wheel in a car. Number 3, they moved it. And now it's within reach and it can be operated in a safe manner. So those are the 3 methods. So let's go through a quick wrap up. Number 1, We focus on quality, value, and safety starting on day one. We conduct checks on the design and feed the results back to the design team. So under quality, we might do something like a peer review, right? Maybe it identifies a hydraulic pinch point that the team missed. Value engineering, well, we're looking to see whether we can improve the design, give the client more value. So in this case, they came up with an alternative digester mixing system that used less energy. OPMAN, it could be that a valve is out of reach, and the design can use this input to improve the design. Then we can think about, when do we do this? So again, I said it's during detailed design. So you can do an OPMAN best at about the end of 60%, the same when you're doing a Swift or a Hazop. You can do an OPMAN earlier, which can also feed in and assist things, but normally we do it about 60%. And if you think about the other things that we're doing to check the quality of the design, so we have coordination meetings, we're doing value engineering at the beginning of detailed design, and then value engineering at the end, more to look at constructability issues. And we may do some regulatory reviews right at the start of detailed design. Now, I'm often asked this question of, okay, why would you do a Hazop or a Swift? So this is the typical advice people normally get. When it comes to something you've done before with a low risk, you probably use a Swift because of the low risk. And it also then gives you that ability to look at logistics as well. If it's something that has a high risk, something that you haven't done before, something like, let's say you've never done a thermal hydrolysis plant before, or you have a sludge dryer, you may require a Hazop because you really want to go through the process to make sure you understand it and have covered off all the risks. If you've done it before at another plant and you have the Hazop record, then you may say, okay, that's enough, I'm going to do a Swift. That's normally what we recommend. But if you look at that bottom orange box, I recommend you do OPMAN on everything. So let's think, Hazop. We'll use it when the technology is new to a client or a process is hazardous. Swift. We do that when we don't do a Hazop. And OPMAN, we do it on every design. So let's close off. This is my last slide. So again, we go back to that statement. The construction, commissioning, and operation maintenance of our facilities is safer when we think safer day one. And that goes back to what Trevor Klecht told us about. We intend to design safe, we check to make sure we've designed safe, and we learn from our successes and our mistakes. So often the strategies we use to check designs in the water industry are Hazop, Swift, and OPMAN. And that so that we can integrate safety into the design thought processes. Now, I can guarantee that design engineers that participate in these types of checks and evaluations will go back to the office and design differently. So I'm going to leave it with a quote from Trevor Klecht. Try to change situations, not people. We haven't got the right to roll the dice on the safety of the people we're designing plants for. So any questions?
Great presentation, Pat. Thank you very much. It's not something you hear about a lot, so I appreciate you taking the time. We do have a few questions. Let me get those here. I just got to browse to the right part of this system here. All right, here we go. What has surprised you most when doing an OPMAN?
So I did an OPMAN for a pump station. And there were two things about that surprised me. Number one, because we were supposed to do a SWIFT afterwards. But by the time we finished the OPMAN, we didn't need to do the SWIFT because almost all the risk and hazards, all the hazards were actually for the staff, not the plant itself. The plant itself, the design was sound, it was to the staff. And a lot of those hazards were related to the maintenance of the heaters in the facility. So over and over again, we got into this situation in the OPMAN where the operator said, I cannot maintain that without violating the health and safety practices of my employer. So that surprised me.
All right, the question came in wondering if Stantec provides the facilitator services, if a client needs help with a SWIFT or an OPMAN.
Oh, absolutely. Absolutely. And we have done so.
Okay, good question. Here's a new one. Could you give us an example of when a SWIFT identified a non-process hazard? We talked a lot about, obviously, process, but things that are non-process related.
Yes, we were doing it on a source separate organics anaerobic digestion plant. So it was taking basically food waste from the households. It was being trucked to the site and then it was being processed and digested. Because up here in Toronto, you know, this area of Ontario, 20% of Canadians live between Hamilton and the other side of Toronto, right? The rest of the country is pretty empty. So there's a lot of stuff, right? So what surprised us is that one of the major risks was the movement and the management of the vehicles on the site, particularly when they came in to dump. So we ended up, out of the SWIFT came a whole strategy of traffic light systems to ensure that the trucks parked in the proper spaces and they didn't park in front of the doors when a truck was in the bay. So that was a non-process, more of a logistics risk and hazard that we identified.
All right, makes sense. Can you give us an example of a risk that was not anticipated at a wastewater treatment plant through using these processes?
We were doing a plant. I was doing a plant in England, and the way it worked is when it had quite an extensive fat skimming process, and the fats were skimmed into a hot water tank, and the fats were all dissolved in a high temperature hot water, and then that was pumped over to the digester. What surprised us as we went through is that we had missed the Legionella risk. So when the person, because it was right at the temperature that Legionella will grow, that we hadn't thought through the proper health and safety safeguards to ensure that when the person who opened that tank would be aware of the risk. That also showed up at another facility again, where we were heating water. We had warm water and we were storing it in a tank that we hadn't thought of that Legionella risk. So that was one of those that kind of slipped by the designer, and then we caught it, and then we were able to put the safeguards in place.
Good, good. Could you just another question came in here, if you could, a quick summary again of maybe the time of each of the three that it takes to go through these, maybe on an average plant, just so they can have a better understanding of the monetary investment, I guess, is probably what it's wondering.
So most of the SWIFTs I've done have taken a day. I haven't done whole plants. We haven't done whole plants. We usually do parts, but we did a whole aeration tanks, clarifiers, chemical systems, and all that in all one day. Hazop would have taken 2. OPMAN, I found OPMAN takes about the same time as a SWIFT. Although if you do them in series, what you'll find is you'll identify many of the risks in the OPMAN study, and then as you go through the SWIFT, it goes quite quickly. So when we did this pump station job, I think the SWIFT took 30 minutes, because by the time we finished the OPMAN, which took most of the day, we have uncovered most of the rest. So it's usually a 2-to-1. A Swift will take 1 day and Hazop will take 2. I know people speed up Hazop, but actually then they're actually shifting much more into the area of a Swift. So they're doing almost a Swift, but without realizing it. So I don't know if that answers the question.
Yeah, I think so. Just
in the table, in the presentation, in the technique tables, there is an estimate per P&ID for Hazop and Swift.
Okay, great. Here's an interesting question. This will be a fun one for you, Pat. To what extent can these studies be influenced or modified by artificial intelligence? Or will they remain as people-centric, do you think?
I think
Can you predict the future?
Yeah. I think they will be people-centered for a long time, simply because what I find it's the discussion among the people in the room, then because each person, I mean, let me explain it this way, each person is in their little silo. So the electrical designer, the mechanical designer, the operator, they're all focused on doing their jobs, right? When you put them in a room with a good facilitator and they start talking, it's interesting to see how people, when they're talking and communicating, things come up that no one thought about. And I don't think you can get that with artificial intelligence because of that dynamic. People often don't know what they know. And that's the whole, it's interesting, and that's that whole fundamental principle of psychology is the basis of the integrated design system for green buildings, for example, that you can have a structural engineer talk to an alderman, and the alderman actually says, I think there's something here that you need to look at, right? Even though he's not a structural engineer, he saw something that the structural engineer didn't see because the structural engineer is too close to it. So when you put operations in the room with engineers and they start learning to talk to each other and start understanding or appreciate what each does, it's amazing how good you can make that design. I guess I'm a bit passionate.
No, that's a good point. We operate a plant over in Lincoln, California, and I've had some conversations with our team there, and they will definitely tell you the same thing.
Yeah.
So I appreciate that. Kind of a general question here, though, I think makes a lot of sense. So I think everybody's probably heard of Hazop and has done Hazop. Why is that still so popular, and why are Swift and OPMAN not as well known?
Yeah, that's a good question. So Hazop, so the water industry, okay, you need to understand something about the water industry. The water industry borrows from other industries all the time. And there's the EPA documents that were published in the early 70s where they looked at different industries and said, okay, yeah, we could apply that technique to our industry, right? Water is a process industry, but not as process as it's a chemical. And it's a manufacturing industry because we do produce a product, but it's not like making an iPhone. So we borrow. And so when people were looking for a method to assess process risk, there were books written on Hazop, right? If you wanted to learn about Swift, you would have had to go into a general book on different risk analysis techniques, right? So I learned about Swift and OPMAN working for a large privatized water company in the UK. And it was feedback from their staff that they developed Swift, and then it was feedback from OPMAN that they developed OPMAN. And so they were kind of the pioneers on that, but they haven't written a book. So I think that's why you see Hazop more than Swift and OPMAN.
I guess following off of that then, in your experience, have you found clients willing to invest in Swift and OPMAN as opposed to a Hazops and open to the concept if they haven't used it before?
Oh, yes, absolutely. Particularly because Hazops are twice the cost, right? They take twice as long. And, you know, people and the people that go to attend them complain because they said, this is ridiculous. It's not that hazardous. We got nothing that blows up, right? We don't have anything that blows up, right? So is there another way of us, and we're missing risks, right? We're not talking about the movement of the screening bins or the movement of the trucks, right? And so yes, once clients understand, and we've had this with City of Toronto. City of Toronto was quite willing to do they did actually the first major OPMAN in Canada, and Swift. We adopted Swift on a number of projects. So looking at basically you look at what you're doing, you're looking at the risks, and then you say, what is the most appropriate method for us to check this design?
Great. All right, I'm gonna actually give everyone the ability to unmute themselves now, if they would like. And they can then, if you'd like to, you can comment or ask a question live. You're also welcome to continue to ask questions using the questions chat box, but you now have the ability to unmute yourself if you so choose. Thank you for the questions so far. They've been great.
Yeah, thank you very much. Well, if we got time, I can close it off with a story. What actually got me passionate about this. I sat with a senior mechanical designer who I had a great respect with. And one day we were just talking, and he told me about a situation where he was involved in the design of a plant, and it was enclosed, and they had put covers on, but they never really thought much about the covers. They chose the cheaper ones, and they said, yeah, we can take them on and off, right? What they didn't think about is what the operator did every day. And he said to me, this one incident has changed his attitude towards the design. He said that operator found it so onerous because he had to check the process. And so finally, what ended up happening is he took most of the covers off and left them off. Well, the HVAC was never designed for this. He is now sitting at home with 1/3 of his lung capacity on permanent disability. And the guy said, that changed my view towards safety. I never, ever want to be in that situation again, where I had anything to do with the design, where somebody who is in the front lines doing the work is now hurt because we didn't take something into consideration. So that whole discussion really shook me up and made me start thinking about what I was doing as a designer.
Yeah, I guess that makes sense. All right, I'll do a final call for questions and see if anybody else has anything else. All right, well, great. Well, thanks everyone for joining. I really appreciate you being part of the webinar. Again, you'll get a certificate for PDH submittal. And if you look in the chat function, you'll see a link to our calendar for our upcoming webinars. And we're also posting a link to where you can find recordings on our website. And again, you'll get a reminder from GoToWebinar of where you can see the recording as well through them. So with that, I will end the webinar for everyone. I hope everyone has a great day.
Yeah, thank you very much.
Thanks again, Pat.
Okay.